Hi thinkers, welcome to the Cracking the Coding interview course on ThinkX Academy. In this video, we are going to solve the LeetCode medium problem, which is the deepest leaves sum problem, and this actually is a problem related to binary tree data structure. So I will show you the approach of this problem, and I will also write the code here in the IDE of this problem. So let's start with the problem. It says that we are given a root of a binary tree. So let's say we have this example. We will be given a root reference to the binary tree. What we wish to do is we wish to return the sum of all the values of its deepest leaves, right? So first thing that we quickly understand here is that we are concerned with leaves. So we will have to write a condition where we can check whether we have a leaf or not. So you can see that here we have a leaf, here we have a leaf, and here also we have one more leaf, right? So we have 3 leaves here, but you can see that we are not concerned with this leaf, which is 5, because we have 7 and 8, which is deeper than this, right? So 7 and 8 is actually much deeper than this, or we can say that at 7 we have a different kind of height or depth, right? So here we can see that height of the tree is 4, here the height is 3, right? So we are concerned with the deepest leaves. So these are the 2 leaves which are at the deepest positions, which is 7 and 8. So if I do the sum of these leaves, we will get an output of 15, and we need to return that in the output, right? So you can see we have 15 here, right? So here we have the public int deepest leaf sum function. We are given the root node reference. So the question is, how can we actually try to get this leaves, right? How can we actually get the maximum height and the leaves at that position? Now the answer to that is we can perform any type of traversal, and at each and every recursive call we are going to maintain a variable which we will call as a height variable. So at each and every position I will maintain a variable height, and initially this height will be equal to 1 for our root node. So we can perform any traversal. In this tutorial I'm going to use inorder traversal, right? So inorder traversal is very simple. It makes a recursive call to the left part, then it visits the node, and then it makes a recursive call on the right part, right? So this is how the inorder traversal works in a binary tree. So at each and every call, what I'm going to do is I'm going to increment the height variable. So for each and every function, inorder function, I will have 2 information. The first is the root, and the second one is the height, right? So every call to this recursive function, we will give 2 parameters, root and height, so that at each and every recursive call, I'll be able to understand what is the height, right? Now we will start with the root reference. The inorder traversal first goes to the left part. So left is 2. At this position, whenever we move and make a call, recursive call to the next part, so we can see that in order, we will first make a recursive call to the left part. We will increment the value of height by 1. So height will become equal to 2 in this case, right? So this will actually make a call to inorder function with root as 2, and height will be also 2, right? Now again we know that it will recursively go to the left part. Again it goes to the left part, and it is going to make a recursive call to the inorder function. The value of the root will be 4, and again we are going to increment the value of height by 1, right? Similarly, we will again go left, and we will again increment the height, and now height will be equal to 4, right? Which I have already written here. Now we will backtrack, we will visit the node. So here you can see that we have null position, and here we also have null position. So at the left and right part we have null node, so it means it is a leaf node. So we are going to make sure that this traversal ends whenever we reach a position where we have a left part or right part as null. So that means it is a leaf node. So at the leaf node I'm going to calculate the height, what is the height, and I'm going to compare it with a max height variable, right? So I'm going to maintain a variable which is max height, and it will be actually equal to minus integer min value, which is minus infinity, you can say. We'll keep comparing it with this, and whenever we get a more promising value, we are going to reassign max height. So here the max height will be reassigned to 4, right? Then what we will do a backtrack. So the algorithm inorder traversal will backtrack, and it will now try to visit the right part. Now you can see that right part is not here, so it will again backtrack to the previous node, and now it will visit the right part. You can see we have a right position, and this 5 node is actually you can see it is also a leaf. What is the height? Height is 3. Is it greater than max height? No. So we are not going to reassign max height, right? So now what we will do, we will again backtrack, and again we will visit now the right tree, right? Now to this right part, we will again explore the left part, but left subtree is not available. So we are again going to move to the right subtree, and we'll keep doing that. And at each and every position, we keep incrementing the height by 1, right? So Now here you can see that we have again height and it is equal to the max height. So at this position we know that our max height is actually 4. Now what we can do is we can use this information to actually maintain another variable which we can call it as max sum, and initially the max sum will be equal to 0. So whenever we get a max height, whenever we reassign the max height, I will just add the value at that position, right? So you can see height was equals to 4 at 7. So I will reassign max sum as 7. Then again at this position the max height will be reassigned because height is actually 4, so it is actually equal to the max height. So again I'm going to reassign it by doing 7 plus 8. So 7 plus 8 will be equal to 15. Things will become more clear when I will write the code. So let's see this in action. So first I know that in this program I need 3 variables, which is the max height, it will be equal to minus infinity. Then we need a variable height and a max sum, right? We need these 3 initializers, and now we will make a call to inorder function, and you can see that this inorder function has 2 variables, one is root and the height. So at each and every recursive call I know what is the height and I know what is the root, right? Now at the end we will return the max sum, which is the maximum sum of the deepest leaves, right? Now let's define the inorder Dfs function. So here you can see we have a public void inorder Dfs function, and you can see that we are giving the root and height here, right? The first thing we need to do is write a base case. So whenever we reaches a null node we are going to return, right? So whenever we reach whenever the root becomes null we are going to return. The second thing is we need to increment height by 1, right? So whenever we make a call to this inorder Dfs function, be it on the left part or the right part, we don't care. Whenever we make a recursive call, it means we are actually trying to move to the next element, and when we try to move to the next element of the binary tree, I will increment the value of height by 1, right? So height was initially equal to 0, as you can see here, and here the height becomes 1, right? So for our source node, which is the root node, which is 1, the height becomes 1. Right, now let's move on to the next important thing, which is to make a inorder Dfs function call, which is a recursive call to the left part, right? So we know that in a inorder traversal we recursively go to the left part of the tree, so we keep going to the left part and then we will actually do visit the node, and then we will move to the right part, right? So now let's see what will happen when we reach the middle a particular node. So at backtracking we will check whether a particular node is a leaf node or not, right? So at every backtrack, whenever we reach here, we are going to check whether the left and right part is equals to null. So if both these conditions are true, that it means that the root which we where we are at is a leaf node, right? So in that case what I'm going to do is I'm going to check whether the max height is less than height. So if that is true, it means I need to reassign the max height as height, and at that position I'm also going to reassign max sum equals to root dot value, which you can see is 7 in our case. Right, now what I'm going to do is I'm going to say that if the max height equals to height, so you can see that max height was 4 here, and at this position, which is at 8, height is again 4, right? So we need to handle that case. So whenever the max height becomes equals to the height, we are going to make sure that we increment the value of max sum by max sum plus root dot value. So max sum was 7, and we increment 8 also, so we get 15 here, right? Now what we are going to do is we are going to make a inorder Dfs call to the right part of the tree, right? So we make a inorder Dfs call to the right part with the height, right? So at each and every position it will make a call to the right part and it will increment the value of height by 1, and here it will keep checking whether we are at a root node or not, which is the leaf node or not, right? So it checks whether root is a leaf node by this condition, and then it makes 2 checks. The first one is to check whether max height is less than height. Then we are going to reassign max height and max sum, and whenever we get a leaf node which has the max height which is equal to the max height, we are going to add it to our max sum, right? We'll keep doing this for each and every node, and at the end we will return the max sum. So this program is also given on our website thinkexacademy.com, and I will give the link to that in the description also. So that's all for this tutorial. Thanks for watching.